Howdy, my name is Bill Bachelor. I'm a professor in civil engineering at Texas A&M, and I'll be presenting now the review for the Fundamentals of Engineering exam, at least the portion dealing with computers and numerical methods. I've taught the Computers and Numerical Methods course in the civil engineering department for several years and thoroughly enjoy it. I also use computers quite a bit in my own research, so it's an area that's very interesting to me, and I hope you'll find it interesting as well. We'll start giving a brief overview of what we plan to talk about today. We'll start with a brief introduction, talking about what to expect in the Fundamentals of Engineering exam with respect to computers and numerical methods, and then we'll deal with computers and numerical methods in more detail. As you've probably been told and have learned, the Fundamentals of Engineering exam is divided into two parts. One part in the morning, one part in the afternoon. The morning session, everybody will be taking, and we'll focus on computers. There will be 7 questions out of the 120 in the morning dealing with computers. In the afternoon, you will be taking different exams based on what area of engineering you choose to specialize in. If you choose the general exam, you will be having 3 questions out of the afternoon 60 that all focus on computers. So if you choose to go the general route, all of the questions you'll be dealing with are going to be on computers. However, if you choose to take one of the disciplinary afternoon exams, then you will have questions that may deal with computers or numerical methods. For example, the chemical engineers will have 3 questions out of the afternoon 60 will be on computers and numerical methods. The civils will also have questions on computers and numerical methods, but we'll have 6 out of the 60 in those areas. So the mix of questions to expect depends on the type of exam that you'll be taking. My understanding is that most of you are planning to take the general exam, so in the review today we will focus on the computer portion. We'll cover that first. Those of you that are planning to take the general exam can then ignore the rest of it. Those of you that will be taking an exam that has parts directed towards numerical methods can stay around and review that material. All right, before we get started in the review, I'd like to give you a little idea of where the material has come from for the review. And what you see here is a list of the sources that I've used. Primary source is the reference handbook that comes from the National Council of Examiners for Engineering and Surveying, the people that are making up the exam, so that's probably the most important thing you'll be dealing with. The other important source is a publication of sample questions, again put out by the people that are going to make the FE exam, and then 2 review manuals that cover preparation for the FE. So you'll see as we go through the material that there are a number of places where the material has a reference to one of those topics. All right, looking now at the bottom of the first page of your handout, we'll begin the review of the computer section. The first thing I want to do is focus exactly on what expectations you should have for material to be covered on the FE that's directed towards computers. This comes directly out of the reference handbook that defines the computer knowledge you're expected to have. It says that examinees are expected to possess a level of computer expertise required to perform in a typical undergraduate environment. So it's saying you need to be able to do the things that you should be done when you were an undergraduate. Thus, only generic problems that do not require knowledge of a specific language or computer type will be required. Examinees are expected to be familiar with flowcharts, pseudocode, and spreadsheets. So those 3 are the major areas that you need to be concerned about: flowcharts, pseudocode, and spreadsheets. So we'll spend most of the time focusing on those 3 aspects. Some of the review manuals also discuss other areas of computers, such as binary numbers, and combinational logic, Boolean logic, and so forth. So we will spend a little time reviewing some of that material quickly, since it may show up on the exams, but I think that material should take a lot less of your time in your preparations. So flowcharts, pseudocode, and spreadsheets are the most important areas that we'll be dealing with. All right, let's then review quickly material on flowcharts. Right? This will be at the top of page 2 of your handout material. So this just summarizes the symbols typically used in flowcharts. The terminal means this would be at the beginning or the end of the program, telling you where it starts, where it begins. The logic flow is represented by arrows, indicating the steps that you would logically go through the program. Processes where calculations are made or somehow the data is being manipulated will occur in a box. Information and data coming into the program would be represented by a four-sided slanting box like this. Decisions are made in diamond-shaped symbols, and that decision could be comparing two numbers, asking some question about values, somehow making a decision in the logical flow. So coming from a decision point like that, you would branch to different parts of the program based on making some choice that one number is greater than another number, that one variable is equal to a given value or greater than a given value, and so forth. So then this is the point where you're able to have the program go in different places depending on what you want it to do. The other symbol would represent an off-page connector. You can't get all of the flow charts necessarily onto the single page, so that this gives you a way to say, all right, now the logical flow is going to continue on another page. And finally, an on-page connector would mean that the logical flow of the program is going to be shown in another position, but it's going to be on the same page. So if you had, say, a flow chart that would be on a number of columns, you would have an on-page connector at the bottom of the first column, at the top of the second column, indicating that the logical flow is moving from the bottom of first column to the top of the second column. All right, there could be a number of different kinds of problems that are associated with flow charts. One type of problem might be just asking you to identify the kinds of symbols used in flow charts. An example would be here, where the question is asking what operation is typically represented by the following program flowchart symbol. So you can look at that and you see that the shape is of a diamond. That's going to be a decision point where you're going to make some comparison and do some branching. So the answer would be, in this case, D, branching. It doesn't represent processing. It doesn't represent input-output. It doesn't represent storage. Right? Another example of that kind of a problem would be this, which says, which of the following program flowchart symbols is typically used to indicate the end of a process or a program? And you can look down and see, well, we're going to be doing branching there. We're going to be doing some sorts of calculations there. This then is a terminal. It would be at the front or the bottom of the program. So the answer then would be C, termination represented by a symbol C. All right, you might also see some problems where a program would be described in a flow chart, and then there would be some questions asking you about what the program does, maybe saying if the value of this variable was set to 5, what would be the outcome of the program, what would be the number. So those types of problems are going to be very similar to the ones that we'll speak about now, having to deal with pseudocode, in that pseudocode is a shorthand version of a program written in not a specific language, but written in general terms that are typical of the kinds of programming statements that are found in various different languages. So the kinds of problems we'll talk about now in pseudocode, some of those could be shown also in flowchart diagrams. So that by just transferring the pseudocode to the flowchart symbols, you could study for both kinds of problems as we go through. All right, so let's start then looking at some pseudocode as, again, summarizing the types of things that you would see in pseudocode. All right, again, pseudocode is a way to represent a program in generic kinds of statements that are not specifically associated with any language. All right, so you don't need to know Fortran or BASIC or Pascal or C to understand pseudocode. They're related to, if you know any of those languages, you should then be able to recognize how the pseudocode statement maps into a statement that would be in any of those particular languages. Some of the pseudocode statements are very similar to specific language statements. Other are more general. But you should be thinking of whatever your background is, what other kind of programming language you are familiar with. Look to see how the pseudocode maps into the programming language that you know. That may help you understand how the pseudocode works. All right, let's review just some of the types of pseudocode statements that you have. Typical assignment statement, where you are assigning a value, in this case 3.4, to a variable x. So you use an equal sign in the pseudocode, such as is used in many language. But keep in mind that it's not the same thing as an algebraic equal sign. It means basically evaluate what's on the right-hand side, store it in whatever variable is defined on the left-hand side. So that a statement such as x plus 1 equals 3, which would be valid in algebra, wouldn't be valid as a computer assignment statement. Right? Input statements indicate that some value is coming in outside the program into the program. So this could be input from a keyboard, it could be input from a tape, from some other source. But somehow the value is coming into the program. This then allows you to use the program for many different applications. So what that means then is that the value has been assigned to the variables x and the variable n in this example, much like an assignment statement. So those variables will now have values. In your example problem, sometimes you might have a problem where the problem specifies that the input value for x is a given number. In other cases, it might not specify exactly what that value is, so that then the answer for your problem would be defined in terms of x, just as an algebraic equation. Right. The next pseudocode statement is for next loop. Much of the work that's done in any computer program is done in loops. That's the real power of programming. You're able to get something done over and over again efficiently. So then a lot of the processing and a lot of the problems that you'll be dealing with will be done in loops. In this example, you have a loop in which a variable index I goes from 1 to a value of n, and then between the for statement and the next statement, there would be a series of statements that are executed sequentially, and you go around that loop, in this case n times, until the index reaches a value of n. All right, other kinds of loops are while loops. All right, in pseudocode, you could express that as do while with an end-do. All right, so then a statement example would be do while a is less than 3.4. You then have a series of statements below that, ending with the end-do. So then that means that while, or as long as, the value of a is less than 3.4, continue to execute those statements in the sequence. When you get to the bottom, go back up to the top and check the value of a again. A related but slightly different kind of loop is a do until loop. And this means that, again, you have the do until statement with some statement that is able to be evaluated as true or false, and then a list of statements finishing with an end do. This means that you continue to execute the statements in a sequential manner and a looping manner until the value of, in this example, until y is equal to or greater than 5.0. Another important kind of branching is a if statements, if else end if being the form in pseudocode. And this then allows you to make a number of different choices in the program. For example, in this case you would have the statement if I is equal to 2, then a series of statements, an else statement, a series of statements that follow with the end if. Meaning that if it is true that I is equal to 2, then execute the statements following the then statement before the else. If it is not true, then jump to the else and execute the statements following the else up until the end if statement, and then continue executing statements beyond the end if statement. All right, let's look at some of the types of problems that you might see in pseudocode. So what we have here is a program segment written in pseudocode. with a series of potential answers. In this case, the program begins with an input statement so that it indicates that some values have been given to the program and stored in variable locations called z and n, so that the program then has a value of z and n, but you don't necessarily know what it is when you're working the problem. Then we have two assignment statements that assign values of 1 to the variables s and t. Then we have a for next loop. All right? So this loop begins with a value of k equal to 1. You then, in the program logic will flow executing each of the statements, getting to the next statement, going back up, incrementing k, and continuing that until k is equal to n. And the last time when k is equal to n, it will execute through, get to the next statement, increment, find that k now is greater than n, and exit the loop and continue executing below the loop. All right, so then the question of this is, what is this loop calculating? What is this program segment calculating? The way that I always attack these is to act like a computer and write down things that happen step by step. All right, so what I do when I do these sorts of problems is to sit down and write down the values of a variable and keep track of them step by step. All right, so when we begin with that loop, we'll have k equal to 1. If it comes down then, the computer will then calculate t. It'll calculate t by evaluating what's on the right-hand side of the expression, and that is the value of t, which begins at 1, times z, which is a variable that we don't know the value of, divided by k, and at that point k is equal to 1. So at that point t is assigned the value of t, which is 1, times z, divided by k, which is equal to 1. So then the value of t is equal to z. Then goes down to the next statement to evaluate the value of s. S is evaluated as the current value of s, which has been assigned a value of 1, and plus t, which we just evaluated as z. So then, at that point, the value of s is 1 plus z. Gets down to the next k, jumps back up, increment k, k is now equal to 2. Come down, we now calculate a new value for t. The new value of t is the old value of t, which is just z, times z, divided by k, and k is now equal to 2. So we have z times z divided by 2, which would be equal to z squared over 2. So z squared over 2 then is the new value for the variable t. Execution goes to the next step to calculate a new value of s. S is then equal to the old value, which is 1 plus z, plus the new current value of t, which is z squared over 2. So now s is equal to 1 plus z squared over 2. The program continues to go back, increment k to become 3. You then continue and calculate a new value of t, which is now going to be the old value, z squared over 2, times z divided by the value of k, which k is now 3. So we end up with z to the third power times 2 times 3. We come then down, increment s. S is the old value, which is this part, plus t, which is this part, and that continues. So you can see what's happening is s is going to have the value 1 plus z squared plus z cubed over 2 times 3 times z to the fourth over 2 times 3 times 4. And you can see that the 2 times 3 times 4 is going to be equal to n factorial. So that the answer in this case would be 1 plus z squared over 2 factorial, z cubed over 3 factorial, on up to z to the n over n factorial. So the answer in this case would be D. So the key there is to do the problem like you're a computer. A computer keeps track of things. It doesn't keep all of the information floating around. It stores information in specific locations. You do the same thing. You have a little scratch sheet. Keep track of the values of the variables as they change step by step, and you'll be able to keep up with the problems pretty well. All right, another example here, looking at the problem statement, says how many times will the second line be executed. All right, so this then is a program that starts with an assignment statement, assigning a value of 42 to the variable m, then beginning a loop. In this case, it's using just the statement to loop start, just to indicate that loop is beginning. The first thing is that m is recalculated as the current value of n minus 1, so that the number is evaluated, stored in n. P is assigned the value of the integer part of m over 2. Then a branching statement is added. If p is greater than 15, then go to the start of the loop. Otherwise, go to the end. And end is here, printing with an output of printing the statement done. So again, the way to attack these problems is to pretend you're a computer. And the solution to the things that you would be doing, it would be shown here. You keep track of the iteration, how many times you've gone through the loop. When you start, you begin with a value of m equal 42. The first time you're through the loop, after the first calculation, the value of m is equal to 41. Then p is set as the integer part of m divided by 2. All right? If we divide m by 2, we'll have 20 and 1/2. The integer part then is going to be 20. All right? It then comes down and checks, is p greater than 15? Well, the value of p is 20 at that point, so it is greater than 15, so then you go back to the start of the loop. All right? At the start of the loop, then you now are in the loop for the second time. You subtract 1 from the value of n, so it becomes 40. You take the integer part of m divided by 2. m divided by 2 is 20. The integer part is 20. So that then p is 20. You go through, check, make sure it's greater than 15, and so forth. So you continue that, moving down until you get to the point where the value of p is equal to 15. At that point, when you hit p, then since p is equal to 15, it is not greater than 15, so then you exit the loop. So that leaving the program, the value of p will be 15, and you will have gone through that loop 11 times. So the answer then would be D, or 11. All right, so in all of those examples of using pseudocode, what you're trying to do is just pretend you're the computer, keep track of all the variables, how they change, go through it step by step to make sure that you then have the same values that the computer would have. In all those examples also you could have had similar problems by taking the pseudocode, converting it into a flowchart diagram, and have questions asked about the flowcharts. All right, now I'd like to move on to the third major section on computers, dealing with spreadsheets. I suspect many of you are very familiar with spreadsheets. My limited experience in looking at the exams is that a lot of the problems are spreadsheet oriented, because at least at A&M, use of spreadsheets is a major way that undergraduate engineers are dealing with computers. So it is, I think, an important part. I'll just briefly review some of the basics of spreadsheets, emphasize some of the things that tend to show up more, and then go through some examples of spreadsheet type problems. All right, just as a brief review of spreadsheets, first a spreadsheet is going to be organized in cells, and those cells are organized in rows and columns. All right, so then a row and a column designation allows you to identify a individual cell. All right, what's a cell good for? Well, you put things in it. The types of things that you can put in cells are numbers. You can also put labels, just alphanumeric information, like a name of something. But the real work comes when you have a spreadsheet cell that does something, that has some expression, that does a calculation in some case. So those expressions are going to be numbers or references to other cells separated by different operators. And the typical operators that you see are the algebraic addition, subtraction, multiplication, division, or exponentiation. All right? So that those operators act on numbers or cell content. So in effect, in a spreadsheet, the cell address acts like a variable in a Fortran program or other computer type of program. So then you're just replacing variable names with cell addresses. And there's similar sorts of things. In a computer program, the variable name represents a memory location where some value is stored. In a spreadsheet, the cell address tells you where that value is stored. Right? Other things that are important in expressions are that you can have functions. So this gives you a lot of power in applying it to engineering operations, because you can use things like e to the x power, logs, all the trigonometric functions, absolute value functions. Right? Exactly what functions you have in your spreadsheet depends on the kind of spreadsheet that you have, and it's not really too important. You shouldn't expect to have very specific types of functions that are particular to just a few spreadsheets. You'll probably have problems that deal with the standard sorts of things like trigonometric functions, exponential functions, and so forth. All right, but probably the most important thing to keep track of when you're dealing with spreadsheets and spreadsheet problems on the FE exam is the difference between a relative address and an absolute address. All right? You need an address to identify what cell you're talking about in a formula. All right? The cell address then represents the variable name. It will be defined as the row in the column of the cell, and normally a letter and a number. All right? But there's two ways that you can identify that cell. One is called a relative address. The other is called an absolute address. And the differences are very important in when you copy a cell to other cells, how that address is copied into the other cells. And there have been several examples where spreadsheet problems are specified where you are told to set up a spreadsheet by putting in a certain formula and then copying that formula to other cells, and then the question asks you what the result of one of the cells is going to be. So it's important to understand the difference between relative addresses and absolute addresses. All right. A relative address means that the cell address is stored in a way that defines it relative to the cell that is put in. In other words, if you define a cell as with a relative address, what the spreadsheet actually stores is information for that cell in terms of the cell in which you put the address. I.e., you might say that it's the cell that's 2 columns over and 3 columns up. It doesn't say specifically that exact cell. It just says whatever cell is 3 columns over and 2 rows up. So a relative address is typically what you put in if you just put in a column and row address. Right? If you don't specify it as being absolute, it normally will be considered a relative address. All right, an absolute address is different in that it specifies exactly one address. So if you put in a formula with an absolute address and then copy it, when you copy it, the cell that you copy it to will have a formula referring back to the exact same cell, not the cell that's 2 columns over and 3 rows up, but exactly the cell in which you originally entered the address. So the difference is relative address is copied, and the reference then becomes the same in relative position. An absolute address refers to the exact same cell that it originally referred to. All right, let's then look at some example problems that you might see for spreadsheets. Okay. Here we have a problem saying that in a spreadsheet, the number in cell A4, all right, A representing the column, 4 representing the row, so that then is defining where that cell is, and the contents of that cell are set to a number whose number is 6. Then a formula is put into cell A5, and that formula is saying set the value of cell A5 equal to the value that's in cell A4 plus the value in A4. In this case, the $sign indicates that the second reference to cell A4 is an absolute cell address, where the first reference to A4 is a relative address. So here we have a relative address plus an absolute address. All right. So in that cell, both of those will refer to the same cell. They'll both refer to whatever value is in A4, which was set up to 6. All right. The problem then specifies that that formula is copied into other cells, A6 and A7, and then asks you that the number shown in A7 should be most nearly one of these. Again, when you're dealing with the spreadsheet problems, the easiest thing to do is to write them out, pretend you're the computer, do the calculations just like you expect the computer to be doing them. For example, then, we could say in column A, row 4, the problem specifies that the value of that cell is equal to 6. Then the problem specifies that in cell A5, column A, row 5, a formula is placed there that says calculate the value in cell A5 as the value in cell A4 plus the value in cell A4, whereas first this is an absolute address and a relative address. So then the computer would say, all right, get the value in cell A4, which is 6, add the value in cell A4, which is 6, you'd calculate a value of 12. Then it says copy this formula into cells A6 and A7. Right? When that copying is done, the relative address is copied in a relative manner. In other words, this relative address is actually stored, if the computer was using words, more or less as look at the value in the cell that is one cell above in the same column. In other words, this is cell A4, it refers to A5. It doesn't refer only to that cell, it refers to the cell that's immediately above it. So when then it is copied into the cell below it, the value is copied in a relative manner. All right? It still refers to the cell that's initially above it, directly above it. So it doesn't refer to A4, now it refers to A5, which is the cell that's directly above A4. But the absolute address is copied absolutely. All right? So it then, when copied, refers back to the same cell that it initially referred to, exactly to A4. And then when you copy that cell down to A7, again, the relative cell address remains relative. It refers to the cell immediately above it, in this case A6. The absolute address remains absolute. It refers back to cell A4. So then you can calculate, all right, in cell A6, the value is what's in A5, which we calculated as 12, plus what's in A4, which we calculated as 6, so it's 18. In cell A7, the value is what's in A6, which we calculated as 18, plus the value that's in A4, which we calculated as 6, so it's 24. The answer then would be 24, number B. Right, so many of the spreadsheet problems that you deal with are those that are going to hinge on relative and absolute addressing. The others may have things like macro statements where you are going to be doing some sort of calculation similar to what you might see in a program. Let's go look at one of these. All right, here's an example where you're given a small spreadsheet, columns identified by letters, rows identified by numbers, and in each of the cells you are given a value of a number or a formula. Okay? Many spreadsheets have macros, which are just like small programs, and what this problem says is that there is a macro command that or a small program that the spreadsheet is using, and that this is what the macro is supposed to do. All right? So the macro starts with a statement that assigns the value of 5 to m, then takes that value of m, multiplies it by 2, adds 6 to it, stores it in the variable p, and then calculates for the value of a variable n, the value that's in cell D4, and then subtracts 3 times the value of p that was just calculated after taking the square root of p. Right? So then to evaluate this, the question is, what is the value of n in this macro command? So to get the value of n, you need to know what is in cell D4. To get cell D4, you can see it's just equal to the value that's in cell C4. To get C4, you need to know what's in B2 and B3. To get B2, you have to know what's in A3 and C1. And to get B3, you need to know the value of m. So again, the approach is you need to pretend that you're the computer and go through this systematically doing the calculation step by step. Example of that would be shown here. Go through the first part of the macro assigns the value of 5. The macro statement is here, so the first thing it does is assign the value of 5 to m, and then move down and use that value of m to calculate a value of p. So then you know that m is equal to 5, so you calculate 5 times 2 plus 6 gives a value of p of 16. Then you start on n. n is equal to the value in D4, which in this case is C4. So you can first write it out, then substitute the value in D4, which is now C4. And then you look at, well, where's C4? The value in C4 is B2 times B3. Make that substitution. Then look, all right, what's B2? B2 is in column B, row 2. So it's the value of A3 times C1. The value in B3 is equal to m. And the rest stays the same. And then look at what's in A3. In A3, you have a value of 0.5. So it's 0.5 plus the value in C1. C1 is 3. So you have 0.5 plus 3 times m. The value of m, you had assigned a value of 5. So you substitute then 5 for m. Now you have an equation with all values that you can calculate and carry out those calculations, and you end up with a value of 5.5, which was one of the choices. So your answer then is going to be B, 5.5. There can be any number of those kinds of problems in spreadsheets. Again, the strategy ought to be to act like a computer, to sit down, keep track of all of the individual variables, and find out what the computer is doing that you're asked to determine. Okay. That'll then close out the section on computers. Those of you that will be taking the general exam, that's all of the content that we'll be reviewing today that you need to know. Because on the general exam, there are no questions dealing with numerical methods. If you're going to be taking any of the specialty exams, there will be some problems on those exams dealing with numerical methods. So I'd suggest that you hang around, and we'll cover now some of the numerical methods type parts. Okay, before we move on to numerical methods, I'd like to say one more thing about the computer section. In your handout, I have some other sections under computers dealing with minor topics. Those minor topics are topics that have been covered in some of the review manuals that I've looked at, but do not, in my opinion, seem to fit in with the discussion that in the INSYS document on what you're expected to know. In other words, pseudocode, spreadsheets, and flow diagrams. That material is dealing with things like binary numbers, conversions from binary, hex, decimal numbers, combinatorial logic, Boolean algebra, and so forth. And these are some more advanced sort of topics that are more connected with electrical engineering and computing. So some of that material is described in the section of the reference handbook dealing with electrical and computer engineering. It has been covered in some of the review manuals as a topic in computing or in computers. I don't believe that material will show up, at least in the feedback I have from people that have seen many of the exams indicate that it's not a topic that regularly shows up. So I'm not going to go over and review that material. I'd suggest that you look at it. It may help refresh your memory somewhat, and if it does show up, you'll be prepared. But I wouldn't give it much effort or concern in your review process. All right. Now, let's move on to the section on numerical methods for those that won't be doing the general section. All right, there are just a few topics in numerical methods that are covered in the review manual, and then that's going to define the types of problems that you need to look at. All right, what we have here is a part of the handout on page 6, and it's dealing with techniques for solving roots of equations. All right, solving or finding the root of an equation means solving the equation. In other words, finding the value of the variable that will make the equation true or make it correct. In many cases, what's done is to convert any equation into a form of some function of a variable, usually represented by x, that's equal to 0. All right? So finding the value of x that makes the function of x equal to 0 is then equivalent to solving the equation, or in other words, finding the root of the equation. Right? There are two techniques that you should be familiar with, one of which is expressly described in the reference handbook, and we'll go through that. That's called Newton method. Another technique which is not expressly in the handbook but has shown up in some review materials, and you may make the argument that you really don't need an equation to do this, so that it might show up even without having an equation in the handbook. But we'll focus first on the Newton method. The source of this is the reference handbook, the mathematics section in page 18, and the way it's presented is as shown here. Right? So what you're trying to do is find the root of an equation represented in this symbol by p of x, and the reference handbook shows it as a polynomial equation. All right? Keep in mind that any equation of x could be solved using Newton method. It does not have to be a polynomial, but that's probably one of the most common types of equations that is solved with Newton's method. Right, so in the reference handbook, the problem is stated as to find a root of a polynomial that can generally be described in this way: the value of x raised to the n, a coefficient alpha 1 times x to the n minus 1, and so forth. A couple of notes about this equation. First of all, that it is presented as being specific for polynomials, but it could really be applied to any function of x. There's also unfortunate confusion in the nomenclature, so I'm just going to point this out to help you be sure. The manual uses alpha to represent these coefficients in the generic polynomial, and uses a to represent an estimate for the root. All right, those are different things. These are constant values that define the function for which you're trying to find the root. The a's are estimates of the root. All right, so this technique is a sequential technique where you begin with an estimate, a guess for the root, and that you sequentially come up with better and better estimates for the root. All right, so those sequential estimates are represented by A. The alphas represent known coefficients in the polynomial that you're trying to find the root for. All right, also, the last term is represented by alpha n minus 1, but it really should be alpha n. That's really not a big concern, but if you get involved in it, you may want to know that. All right, let's look a little bit about how Newton's formula works. As I said, it's a sequential formula. To use Newton's method, you have to have a guess or an estimate for what the root is going to be. How well Newton's method works depends on how good that initial guess is. If you've got a good initial guess that's pretty close to the correct root, then you'll probably get there pretty quick. It is quite possible to guess an initial estimate for the root that is so far off that you won't converge. All right? So that Newton's method does not always work. All right? The closer you are with your initial guess, the better the method will work. All right, so what Newton's method needs is you need to calculate the value of the function for which you're trying to determine the root, the piece of x, and you need to be able to calculate the first derivative of that function. Both of those evaluated at x equal to the jth estimate. All right, this nomenclature, the subscript I represents which root you're trying to find. In other words, in a polynomial, there are several roots, several different values of x that will make that equation p of x equal to 0 correct. All right, so there are more than one root of the equation. The subscript I represents which of those roots you're dealing with. The superscript j represents which estimate. All right, so you start with a guess, an initial guess, and then improve that initial guess sequentially. All right, the j superscript just represents which guess you're talking about. So make sure that you realize that that superscript doesn't mean raise it to that power. It's just an index indicating which estimate of the root you're dealing with. All right. So Newton's method works by evaluating the function and the first derivative of the function at a value of x equal to the current estimate, the a super j. All right. and then subtract that ratio from the current estimate of the root to calculate the new one. So you begin with some guess, all right, say j is equal to 1. You calculate the function p of x at x equal that first estimate. You calculate the second or first derivative of the function at that same estimate, take the ratio, subtract it from that initial estimate to calculate a better estimate. And then you redo it, and you continue until you get close enough. And close enough just depends on the specific problem. All right, let's work an example problem. All right, here we're dealing with finding the root of an equation, x cubed minus 3x squared plus 4x plus 60. So this then is the p of x in the formula. And what you're trying to do is find the value of x such that that function p of x is equal to 0. All right? And this problem would specify that it's on the interval between 5 and 20. In other words, we have a polynomial. There are going to be a number of different roots. This one then says find the root that's somewhere between 5 and 20. All right? So the first thing you can do, you know you're going to have to calculate the first derivative. So then you can take the first derivative of the function p of x. So it's going to be the first derivative of x cubed, which is 3x squared, minus 22x plus 4. So then you've calculated in functional form what the first derivative is going to be. Then you have to have an initial guess. All right? In this case, I just chose to make the initial guess in the middle of the interval on which the root is going to be found. So that initial guess in this case is 12.5. All right, so then we have an initial guess. We want to evaluate the function at that initial guess, divide it by the value of the first derivative at that initial guess, and subtract that ratio from the initial guess. So then if we substitute the function evaluated at the initial guess of 12.5, then we get 12.5 cubed minus 11 times 12.5 squared plus 4 times 12.5 plus 60. And divide that by the value of the first derivative evaluated at the x equal the initial guess. All right, our first derivative is here, so we just substitute x equal 12.5 into that, evaluate then that expression, and we get a better estimate of 10.8. So then our A1 estimate is 10.8. That's not necessarily good enough. We had a pretty big jump between our first guess of 12.5 and our first improved estimate of 10.8, so we'll do it again. All right? We evaluate the function p of x at the value x equal 10.8. We evaluate the first derivative at a value of x equal to 10.8. Subtract that ratio from the estimate 10.8, and we come up with 10.1. And again, there's a fairly good estimate there, fairly good difference. We'll then go through and do it again. Again, evaluating the function at the estimate 10.1, evaluating the first derivative at that same value, 10.1, take the ratio, subtract it from the estimate, now we get to 10.0. So you can see we're getting closer and closer. Depending on the listing of the different options that you have, you may need to continue more than once. The problem may also specify to use 2 iterations of the Newton's method to solve a problem, so that you would then stop after a certain number of iterations. Right? Other way to do the same thing, to solve a root of equation, is called the bisection method. Right? The bisection method doesn't require as complicated a formula, and it's a very simple idea. And the idea is that you start with a interval where you know the root. So if we're, say, trying to find the root of an equation that's going like this, so we want to find that value right there. If we start with some interval that we know contains the root, and let's just say that we'll call that interval the distance between x sub L for the lower limit and x sub u for the upper limit, we know that the root here is somewhere between that interval. So the bisection method needs to have an interval defined by an upper and a lower value that contains the root. All right? If you can't come up with an interval that contains the root, you can't use the bisection method. All right, so what you do is you have that interval. The bisection method just says, all right, calculate an improved estimate of the root by splitting that in half. And I've drawn it such that that's going to be very close to the root. But let's say this is, the midpoint. So then we split it in half. All right, now we have two subintervals. All right, what the bisection method does is you have to decide which of those subintervals continues to contain the root. All right? And the way that is done is calculating the value of the variable, or the function, at the two edges of that subinterval. In this case, evaluating it at let's use A nomenclature here rather than X nomenclature to be consistent with what we did with the previous problem with Newton's method, using A as the estimates of the root. All right, so we start with an estimate for the root as being between a lower and upper values. We bisect that interval so that we have a bisected estimate of the root as being, in effect, the average or the midpoint of those two estimates. Then we have to find out which subinterval contains the root. And that's done by evaluating the function at the ends of the two subintervals and then taking the product and comparing it to 0. So then what that means in this case, take the value here, P at A lower, and take the value, in this case we'll call this A sub B, take that value at P of A sub B. All right? What you'll then find is that these are both positive, and when you take the product of them, you'll have a positive value, so it will then be greater than 0. That will indicate that that's not where the root is. You repeat the process for the other subinterval. You've already calculated the value of the function at one end of the subinterval. Calculate the value of the function at the other end of the subinterval. In this case, then, one of the values of the function at the edges of the interval will be negative. So then when you take that product, you will find that it will be negative. It will be less than 0, and that will indicate to you where the root lies. So then in this case, as we've drawn it here, you would calculate that the root lies on the upper subinterval. So then what you would do is retain that subinterval and then redefine the problem so that now we say this will be the lower limit, this will be the upper limit, and we'll go through the process of bisecting it again. So then the bisection method continues to do that process of having a subinterval that contains the root, splitting it in half, determining which half or which subinterval contains the root, retaining the subinterval that contains the root, and continuing that process until you've gotten the estimate for the root as close as you want. In other words, that subinterval that contains the root is so small that you have got as good an estimate as you want. All right? In applications to a problem, it would depend on what the problem states. It could state to use a certain number of iterations of the bisection method. It could also then ask you which of these roots is most close to the value that you would obtain with the bisection method, in which case then you would continue iterating until it was clear which of the optional answers was correct. Okay, let's then move on to another kind of Newton's method. This is on the top of page 7 in your handout. And this is a technique which is designed to minimize a scalar function of several variables. All right? This is found in the reference handbook in the mathematics section dealing with numerical methods. It strikes me as a relatively complex problem to be used on the FE exam. However, it is in the handbook, so I think that it's fair game and you should be comfortable with using it. All right, so let's just review then what's in the handbook. What this numerical method is good for is to find the solution of a scalar function, in this case called h of x. In this case, x is a vector. In other words, it has values of x1, x2, x3. So what you have to do is find separate values of the variable x1, x2, x3, so forth, up to xn in the general problem. that will minimize this function h. Right, so you might think of this h as, say, an elevation. So you need to, and you, in 2 dimensions, you would have, say, x1 and x2 is position vectors, so that you want to find the lowest elevation, and you need to define that as the set of points x1, x2 that defines the lowest point in elevation. Right? Or it could be a number of other types of functions that depend on a number of different variables that you would want to minimize. Right. The formula that is used to minimize it is given in the handbook. And again, this is an iterative process. Right? We're trying to solve this problem by getting an estimate and then sequentially improving that estimate until the estimate gets close enough to the correct answer. Right? So it's a sequential estimate, and it has somewhat the same form of the Newton method that we discussed for finding the root of equation. And in fact, we'll talk about that analogy a little bit more later. But what it means is to start with an estimate of x. In this case, this is a vector function. You'll have a number of different values of x. And then what you see in this term is something that can be calculated. It is the inverse of this matrix multiplied times this matrix. All right? So what you have here is a matrix multiplication between an inverse of this matrix times that matrix, which then will give you a vector which you subtract from the vector of old values of x to get the estimate for the new value. So it's similar in that you see that you have some derivatives in there, so that you're doing calculations based on evaluating the function and its derivatives at the current estimate of the x that solved the problem, and then correcting that current estimate of x's that solved the problem to come up with a new estimate of the x's. And then you would take that new estimate, recalculate these terms to improve that estimate and so forth. So you would sequentially do the calculations until you have gotten the problem far enough along. All right? So to do this problem, you have to then be able to take the inverse of this matrix. And you can see this, if for any number of x at all, this can be a process that will take some time, but it is possible that it could show up. So what you have here is a matrix of second derivatives. Right? The second derivative of h with respect to x1, the second derivative of a with respect to x1 and x2, and so forth. So you can see what defines that matrix. Take the inverse of that matrix, multiply it times this derivative matrix. You then have a vector which you subtract from xk and xk minus 1. All right, some comments about that technique is that the method could also be used to solve a set of nonlinear equations. All right, so just like Newton's method that we discussed for solving the root of equation, it's for solving for a single value of x that makes a function equal to 0. If you have a set of functions that you want to make all of them equal to 0, you could use Newton's method that we just discussed for minimization to solve that problem. In effect, the minimization problem is one in which you are trying to solve a set of equations that are partial derivatives of the function, partial derivative of h with respect to x. Setting that equal to 0 minimizes the function, so that you can also use the same technique just to solve a set of equations. You could also use that same technique to do things such as nonlinear regression, because what you're trying to do in nonlinear regression is minimize the sum of squares. All right. I wanted to review that. As I said, I have a hard time seeing how you can come up with a problem that you would be able or be expected to work in a matter of a few minutes that would use that technique. But it is available, and it's worth you spending some time looking at. All right, let's move on then to the next section in numerical methods, and that has to do with numerical integration. All right, this again is in the reference handbook, the section on mathematics, page 18. We're on about the middle bottom half of page 7 in the handout. All right, so now there are three different numerical techniques presented in the handbook for integration, and you should be familiar and ready to use all of them. All right, in these formulas, the following notation is used. The interval over which you want to do the integration goes from A to B. So these are all problems where you have some function of x, A, and you want to integrate that function between limits of A to B. And that means what you want to do is between those limits of x equal A to x equal B, you want to find what this area is under that curve. Okay? In some cases, you will have only values of the function specified at the start and the end of that interval. In other cases, you may have values of the function specified at a number of different places. All right? So if you have a number of them, you can say delta x then is the distance between the functions that you evaluate. And you can express or calculate the value of that delta x knowing the distance between B and A and dividing by the number of data points that you have. Or, excuse me, in the number of segments. And that's an important differentiation to keep in mind. In this case, represents the number of segments. So in all those formulas that we'll talk about later, in represents the number of segments, not the number of data points. Right, so if you have 2 data points, you have 1 segment. If you had 3 data points, you'd have 2 segments. Right? So in is the number of segments, not the number of data points. All right. The simplest formula that you can use for numerical integration is called Euler's formula, or it's also called the forward rectangular rule. And simply what it does is if you have 2 values of a function, say at x equal A and x equal B, it estimates the area under the curve by, in effect, calculating the area of that trapezoid. Okay? And that's done for a 2-point problem, one in segment, or it can be applied to a number of different segments where you have a number of points. In this case, the formula applies to integrating a number of segments between A and B, where the formula estimates the thickness or width of each of those segments as delta x, and then sums the value of the function at the points x equal to A plus kx, where k is just a index to do it. So what this is actually doing is calculating the area under each of these sub intervals and then adding them all up to come up with the area under the entire curve. All right, so what it's doing is taking this point and using it to estimate the function, taking this point to estimate the area, this point to estimate the function, and so forth. So the forward rectangular rule means that to calculate the area in this segment, it's doing so by calculating the value of the function at the start of the interval and multiplying it times the width, which in this case is delta x, and then adding all of those points up. All right, so here would be an example of a problem there where you would be given tabular values of the function f of x at different points. In this case, x equals 0, you have a value for f of x equal 2, 4, and 8. And the problem would then be to estimate the integral from 0 to 8 using the forward rectangular rule. All right, so what we're trying to do is find the integral from a to b, in this case from 0 to 8, of the function. Applying the formula, it's delta x times the summation of the value of the functions, and the summation goes from the start to the second, or the next to the last point. So in this case, then you would calculate delta x, and in this case, all of the delta x's are equal to 2. And then it's the summation of the values of the function at those points. So in this case, it's the value of 10 plus 12 times delta x equal to 2 plus 7 times delta x of 4. Note that in this problem, there are 2 different values of delta x. All right? To apply the formula, you need to have a constant value of delta x. In other words, there's only one delta x in this formula. So if all your data is equally spaced, you can apply it in one summation. If you have data that part of it is spaced with one delta x, the rest is spaced with another delta x, you have to break out the summation in 2 points. So what that means is you have this function, you have a delta x of 2 and then a delta x of 4. So you have the values of the function here. You're calculating this area, you're calculating this area, and then you're calculating the final areas. Okay. In this case, then, you could end up with a value of 72. All right, let's move on to another way to calculate integrals numerically. In other words, these are techniques that could be applied to the same kinds of problems, and that's the trapezoidal rule. Again, this comes from the reference handbook section on mathematics. The trapezoidal rule is presented first for n equal 1 for one segment, all right, so that then the value of the integral is equal to the delta x times the average, in effect, of the function over that interval. So that here we're trying to determine the area under the curve given 2 points, and what's done is to, in effect, calculate the average point and use that average point, average value of the function over that interval to estimate the area. So you take that average value of the function, multiply it times delta x, and use that to estimate the integral. If n is greater than 1, you can then apply this formula sequentially, and you come up with this formula. The estimate for the integral is delta x over 2 times the value of the function at the start of the interval, plus twice the value of the function at all the internal points, plus the value of the function at the end of the interval. And that comes just from applying this formula sequentially to all those points. Again, to apply this formula in one step, you need to have a constant delta x. Right? So whenever you apply the integration formulas, you need to check to see what is the distance between the points so that you can properly apply whatever technique you have. In this case, you can always apply the trapezoidal rule interval by interval, or segment by segment. Even if all the data has different spacing, you can go in and apply the trapezoidal rule to each of those segments, add up all those sub-areas to get the total area under the curve. All right, so again, looking at that same problem we had before, we're going to integrate from 0 to 8 using this data. We have to, again, recognize that we have a constant delta x for the first 2 intervals and then a different delta x for the last interval. So we can apply the formula for trapezoidal rule for multiple intervals here. In other words, delta x over 2, delta x for the first 2 segments is equal to 2, so it's 2 over 2 times the value of the function at the start of the interval, which is 10, twice the sum of all the internal functions. There's only one in this case, that's 12, plus the value at the end of the interval, which in this case is 7, and then apply a single application of the trapezoidal rule for n equal 1 using one segment to the last section, which is then delta x over 2 times the sum of the function evaluated at the start of the interval and at the end of the interval. Do those calculations and you end up with 49.0, which indicates that you do have different values using different integration formulas. All right, there's one other integration technique that we'll review. This is another one that's in the reference handbook, and it's Simpson's rule. All right, as we go through these, we're getting to integration formulas that are somewhat more complex, but provide more accurate estimates for the integral. Right, Simpson's rule has to apply to sets of segments. So you have to have at least two segments to apply Simpson's rule. Right, with two segments, meaning that you have three functional evaluations, this is the formula. All right, so b minus a over 6, that's the overall length of the segment that you're trying to integrate over. You take the value of the function at the start of the interval plus 4 times the value of the function in the middle of the interval plus the value of the function at the end of the interval. Right? Note that this requires that the spacing between functions in those two segments be the same. All right? And that's a requirement of the Simpson's rule. You have to have equally spaced data, and it has to come in even numbers of segments. All right? So if you have n equal 2, with equally spaced data, this is the functional form that you can use. You can either use it in this form, or if you like it in terms of delta x, you can put it in this form. All right? And that's just based on b minus a over 2 would be equal to delta x. All right? If you have more segments, n greater than or equal to 4, and n is an even integer. All right? So because Simpson's rule is lumping intervals together in pairs to do this calculation, any application of Simpson's rule to multi-segments has to have an even number of segments. All right? So that if that is true, you can apply this formula, which again looks somewhat the same, delta x over 3, the value of the function at the start of the interval, twice the functions at even values of the index plus 4 times values of the function at odd values of the index, so that in effect you would start with a f of a plus the next function times 4 plus the value of the next function times 2 plus 4 plus 2, and so continue until you add in the last functional evaluation. All right, here's an example of another problem that would require you to use Simpson's rule, and this is a problem in which you have an irregular tract of land, and the problem specifies that you need to determine the area of the tract, so in effect you're calculating the area under that curve. The important thing to note is that the data is given where you have 1, 2, 3, 4 segments, but the segments have different values of delta x. So you have to break the problem down into two parts, apply Simpson's rule to the first part where you have constant delta x of 6 meters, apply it then to the second part where you have constant delta x of 8 meters. The application here, then breaking it down into two parts. The first part would integrate from 0 to 12 meters, applying the b minus a over 6 formula. You'd have b, the end of the interval, minus a, the start of the interval, divided by 6 times the value of the function at the first functional evaluation, in which case is 3.2, plus 4 times the next one, 4.6, plus the last one, 6.5. Calculate that as 56.2. Then apply Simpson's rule again to the next set of data. So you're going to integrate now from x equal 12 to x equal 28. The range is from x equal b equal 28 to 12. Put b minus a in. Put in the first functional evaluation, 6.5. 4 times the midpoint of 4.5, plus the last one, 2.8. Carry out those calculations, you get 72.8. The overall area then is the sum of those two sub-areas are 129. So your answer then would be B, 129.8. All right, so there'd be any number of ways that you could get numerical integration problems in, either just giving you values of the function or setting it up as that last example with calculating a real area. All right, now let's move on to another aspect of numerical methods, and that's solving ordinary differential equations. Right, this again is a section that comes directly from the reference handbook, the section on mathematics, page 18. And what you'll see there is the formula for applying Euler's method to solving an ordinary differential equation. So the problem that you have in solving an ordinary differential equation is that you want to find a value of function, say y of t, for values of t over a given range. And what you're given to work with is a differential equation that says something about how y changes with t. Right? So you have a differential equation that says the derivative of y with respect to t is some function of y and t. Right? So you have a differential equation to solve, and you need to be given an initial condition. In other words, what is the value of y at the start of the interval? So basically what this problem would be is that we're trying to find y as a function of t, and you're given at point t equal to a, you're given a value of the function at that point. So we have this point, and we're trying to solve to find what y is at other points. All right? So this is a numerical method. You're not going to solve and come out with a answer that is an equation. What you're going to do is you're going to solve and come out with values of the function y at different points. So graphically what we're going to do is then break the t variable into different increments, delta t. So then we'd look at a value of t that is delta t away from the initial point, and we want to find out what y is at that point. What Euler's method does is say, all right, you know something about how y changes. You know that slope, the dy dt. Graphically, that means you know what the slope of the function y is going through this point. So if we know what the slope is of y at that point, if we assume that that's going to continue, be the same slope over that whole interval, we can use that to calculate what the value of y will be at the end of that interval. All right, in this case at a plus delta t. Then if we know that, we can calculate using our function here, that we know that the slope is defined as some function we know. We could then calculate what that function is and maybe get a slope like that and use it to calculate the value of y at the end of the next interval, and then continue that as often as we want. So you can choose by specifying what the delta t is, how far you want to go out in each step, how many values of y that you'll specify. All right, so in the Euler method, mathematically what it says is y at k plus 1 delta t, in other words, y at the end of the interval, is equal to y at the start of the interval, k times delta t, where k is just some index to indicate where you are along this line, plus delta t times the function. All right, keep in mind a function evaluated at y at the start of the interval and t at the start of the interval. So you have this function given to you. It represents the slope. You multiply the slope times delta t, add it to the initial value, you get the value at the interval. In other words, you're taking this value, the value of y at the start of the interval, you are calculating the slope, how fast it's changing with t, multiplying it by how far out in t you want to go. That gives you the change in y over that interval. In effect, this distance, you then take that, add it to y, and you get the new value. And you continue doing that until you get to whatever point B you want to stop at. Let's look at an example problem. And this is a problem that requires you not only to solve an ordinary differential equation, but it also has you need to set up the problem. What it's specifying is that there's some tank. It has a given cross-sectional area, and it has a maximum liquid depth. Liquid can be withdrawn from the tank through a pipe, which is a foot below the bottom of the tank, and the flow is regulated by a valve such that the flow depends on the height, the liquid height above the tank. All right, so it says that there's nothing else coming into the tank, and it says to use a center difference approximation to determine the length of time required to load the liquid level in the tank from 11 feet to 9 feet. Right? So first of all, what you in this problem you have to do is you have to specify what the differential equation is that you want to solve, and you do so by applying a balance equation. All right? So what you can balance in this case is the amount of material in the system, and the amount of the material in the system could be represented by the volume in the system. All right? So if you did that, you could show that the accumulation of material in the system is equal to how much comes in minus how much goes out. All right? So and that could be represented as the change in volume with respect to time is what comes in minus what goes out. In this case, the volume in the tank is the constant cross-sectional area times the height of the liquid in the tank. The output flow depends, as specified in the problem, on the height. All right? This was given as the function that specifies the flow going out, and the problem specifies that there was no material coming in, so Q in would be 0. So then, making those substitutions, we end up with this as the differential equation that was specified in the problem. Right. What the problem specified was to apply finite differences, or finite difference approximation to that problem, and the way it was set up, it is easier to do this problem in a Euler-like method, but not in a direct Euler method. So what is done is estimate the derivative as the change in h at any two heights times delta t, and then use an estimate for the h on the right-hand side, which is the average of those two. So this is saying that whatever delta t we're concerned in, it will result in some change in the height. We will use that average height to estimate what the flow going out is in A. We can then simply solve this for delta t, and by rearranging this result, and because the problem asked for how long it would take to go from 11 feet to 9 feet, that specifies the two values of the height. We can plug everything in and come up with an estimate of 47.4 minutes, which was option B in the problem. Right? This problem can also be solved using the Euler method once you set up the differential equation. In this case, since the information is given about the change in elevation and you want to calculate the time, it's easiest to then invert the problem and have it in terms dt dh rather than dh dt, but then you can use the Euler method to solve that. One other part of ordinary differential equations that is described in the reference handbook that you might need to use in a problem is to solve a second order ordinary differential equation using the Euler technique, which is designed to work on first order ordinary differential equations. So you have to then convert a second order ordinary differential equation into a set of first order ordinary differential equations. So in general, then your problem is that you are given a nth order. In this case, we'll work through the example for a second order ordinary differential equation. So in general, a second order ordinary differential equation has a second derivative of y with respect to t squared, perhaps some function of x and y times the first derivative of y with respect to t, plus some other function of x and y, and possibly t actually. Right. Given in part of the problem then is you need to be given the value of y at some initial point and the value of the derivative at some initial point. Right? So in effect, you're giving these values and the second order equation. What you need to do then is convert that into a set of two first order ordinary differential equations so you can apply the Euler method to it. And the technique is just to define a new variable. I'm calling it z in this example. And you define that new variable as the first derivative of y with respect to t. Right? If that's your definition for z, then you can take the first derivative of z and show that it's then equal to the second derivative of y. Right? Then you substitute back into the original equation, substitute that the first derivative of z with respect to t is equal to the second derivative of y with respect to t. Substitute that the first derivative of y with respect to t is equal to z. And now we have an equation which is a first-order ordinary differential equation. All right? So that we have dz dt is equal to something that depends on x, y, and z. All right? The initial condition then is that z at t equals 0 is dy dt at t equals 0, which was specified, in this case, as y prime sub 0. Right? So then we have a ordinary differential equation that is first order, that could be solved with Euler's method. The other equation just comes from the definition that we made for z. We just reverse it. We have a second first order ordinary differential equation that dy dt is equal to z, and that its initial condition y of 0 is equal to y naught. So then we have taken a single second order ordinary differential equation and we have converted it into a set of two first order ordinary differential equations, each with their own initial condition. So then we can apply Euler's method to solve each of those step by step, as long as we are careful to solve them both together. We can't solve one all the way and then come back and solve the others. We have to solve each of them step by step together. We can then repeat that process for higher order ordinary differential equations. And in general, you would repeat the process, defining new variables in each step along the way as the first derivative of one of the existing variables, so that you start with an nth order ordinary differential equations and you end up with n first order ordinary differential equations. But I would suspect that you're not likely to see a problem with more than a second order going to two first order because of the extra time that it would take to do those. All right, one final topic that I'd like to talk about in numerical methods is regression. This is covered in the reference handbook in the section on statistical applications under industrial engineering. It would supposedly then not be something found in the afternoon session except for those people taking the industrial engineering exam, but it is reported to have showed up, so I just want to alert you to the fact that if you see a problem dealing with linear regression and you just don't happen to remember all those formulas, that they're in the book, but they are found in the section on industrial engineering, and it's found on page 100. And so it emphasizes the point that you need to spend some time with that reference handbook. That's the book that you're going to be able to have with you at the exam, and you need to spend some time with it to make sure that you know where the material is in the handbook that you're going to need to use. The better you can, or the faster that you can find that material, the more problems you're going to work, the more time you'll have to check your work, and the better you'll be able to do. But in there, the problem is specified as finding a linear equation of the form y is equal to a hat plus b hat x, where a and b are unknown coefficients at the start. So the job is to find the coefficients given the values of the variables. In other words, normally, you have x and y's as unknowns and a's and b's are things you know. In a regression, the reverse is true. You don't know the a's and b's. You don't know the coefficients, but you have values for y's and x's. All right? In this case, this is the form of the formulas that are in the reference handbook, and they say that they define a hat as y bar, or the average of y, plus b hat times x bar. B hat is defined as this s sub xy divided by s sub xx. S sub xy is a summation of the product of the data points xi times yi over all the data, minus 1 over n. In this case, n represents the number of data points, times the summation of all the x data, times the summation of all the y data. Right? Carry out that, you have the value for s sub xy. Calculate the value of s sub xx as the summation of each x data point squared, minus 1 over n times the summation of the x data points, and that entire summation is then squared. Y bar is just then the mean or average value of the y's, x bar is the mean or the average value of x's. The summation of the values divided by the number of data points. Right. example linear regression problem would be that you're given, say, a set of data for a population of a town over different years, in this case running from 1960 to 1990, and you're asked to use linear interpolation or linear regression to estimate what the value of the population in the year 2000 is. So that means you want to fit an equation that will give you the population as a function of the year, and then when you have that equation, plug in a value of time of 2,000 years and estimate what the population would be at that point. What we have here is a spreadsheet that shows how these calculations would be done, and let me make it a little clearer where everything goes. What we did here is list just the data, the values of X and the values of Y. This is just relisting the data that was specified in the initial problem. And then you know that you're going to have to calculate the sum of the X's and Y's. So then you'd list the data, calculate the product of X times Y, list those, sum them up. You're also going to have to calculate the sum of the X's. So just take the X value, square it, sum it up. All right, so then you have the values of X, Y, the product X times Y, the square of X, and the sum of X, the sum of Y, the sum of X times Y, and the sum of X squared. Then going back and looking at the formulas, first we can calculate the value of X, S of XY. It's the sum of XI, YI. In this case, this long number here, 263 million. All right, then we subtract 1 over n, in this case 1 over 4, times the summation of X, which is 790, times the summation of Y, which is 133001. We calculate that as 336,000. Then use the formula for S sub XX. It's the summation of X squared, which we have is about 15 million here, minus 1 over n, or 1 over 4, times the summation of X, which is 7,900, quantity squared. Carry out that and you get 500. Then calculate Y bar, the average, is the summation of the Y's divided by the number of data points. You get that. Get the average X, the summation of the X divided by the number of data points 4. You get 1975. And then you can calculate B hat, the slope of the linear function, as SXY divided by SXX. So then that is what we've calculated as S of XY divided by S of XX, which you calculate as that number, and then calculate A hat as Y bar minus B hat X bar. All right, we calculated Y bar here. We subtract B hat times X bar, and we end up with this number. All right, so then we have the slope and the intercept of our function. We can then evaluate the value of the function, evaluate the population at a time of 2,000 years. So Y is equal to A hat plus B hat times X. In this case, Y hat is minus 1,297,000 plus the slope 673 times the value of X 2,000, and we end up with the answer, in this case, around 50,000 as the estimate for the population. Right, so that is a problem that you may not see, but it has shown up, and it emphasizes to me that you need to spend some time with your reference handbook to be sure that you know where the information is that you potentially can need to use. In this case, some of that information may be in sections with other engineering specialty areas. In this case, the industrial engineering area. All right, that wraps up the summary I have for you on numerical methods, and I look forward to seeing y'all at our question and answer session in a few weeks.